Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with your video on your ZyBooks Section 2.7. It's Proof by Cases. So this is yet another section in Chapter 2 on proofwriting methods. So far we've seen direct proofs of conditional statements, if P then Q. Proof by contrapositive for conditional statements. Also proof by contradiction. Right? So this is again yet another type of proof, right? A proof by cases, where you're going to have every statement is about a certain type of number or a certain type of object, right? And remember, the domain is the set of all those objects. What you do in a proof by cases is kind of just break up the domain into pieces and do a proof of the statement for each of those pieces. And as long as you take into account everything from the domain, it'll be considered a valid proof. And I'll show you what I mean. So, proof by cases. Many theorems can be phrased as, for every x, p of x. Right? P of x, some predicate, and for every value in the domain, the statement p is true. Where the value of a variable x can be any element from some domain. Sometimes proving such a theorem simultaneously for all elements in the domain is difficult. But the proof becomes much more approachable if the domain is broken down into different classes, like I was saying, the different pieces earlier, where each class can be addressed separately. A proof by cases of a universal statement such as for all x, p of x, breaks the domain for the variable x into different classes and gives a different proof for each class, right? So it's kind of repetitive, but you have to make sure you take into account everything from the domain, right? Show that the statement is true for everything in the domain. The proof for each class is called a case. Right? Every value in the domain must be included in at least one class. Right? So you can have some overlap, but as long as every value in the domain is represented. In a proof by cases, the cases are numbered, and each case begins with case n. Right? And you'll see that when I write out some proofs in a second, where n is the number of that case. The number is followed by a statement of the assumptions for that case. So basically each case is kind of like a mini proof. Right? You're proving the statement is true for each case. So I'll go to a piece of paper and we'll start with this theorem here. A theorem to be proven by cases. For every integer x, x squared minus x is an even integer. Right, so I'll write that out and show you an example, this first example of a proof by cases. Okay, so here's the statement again. The theorem: for every integer x, x squared minus x will be an even integer. Alright, so this statement is about the integers, right? For every integer x. So the domain of x, right, the domain of just the variable x here, is the set of integers. Now, very often for shorthand, and you'll see this in chapter 3 a lot too and later in the course, the set of the integers is represented by like this capital Z with a bar like that, like a fancy Z. And you know what the integers are, right? There's dot dot dot, -3, -2, -1, 0, 1, 2, 3, and so on. Alright, so trying to prove this statement directly without breaking it into cases would be a little difficult. Because when you say, I want to prove this, show that this statement is true, right? X squared minus x will be even for every x. showing that this statement is true, you'd have to pick, for every integer, you have to let, x represent any integer, and then, go to this expression, see if you can express that as 2 times some integer. Remember what it means to be even. So I eventually want to get x squared minus x to be equal to twice an integer. But as is, with just x involved, that might be considered a little difficult. So here are, what I'm going to do is I'm going to break the domain up into pieces. Right? And again, they can be overlapping, they don't have to be. Into 2 cases. Now notice the conclusion, what I'm trying to show involves parity. All right, remember parity was whether or not you're even or odd. So I look at what I'm trying to show, and you should always keep in mind what you're trying to show when writing a proof. And what I'm trying to show involves the parity of an integer. So a natural way to break up the domain here is by parity. I will break up the domain, break up the integers by parity. Meaning, the evens and the odds. Right? That would be a very natural way, again, because I'm proving a statement about parity, right, about evenness. It would be a natural thing to do to break up the domain into 2 cases, one where x is even and one where x is odd. Right? So here's the proof, and this is again an example of a proof by cases. So I start off just like any other proof. I'll write the word proof with a colon to indicate that the proof has begun. But it's a proof by cases. One case, I'll write case 1 and another colon. And this is like a mini proof, a proof within a proof. Right? Case 1, this is this statement's about every integer x. Well, what if we just look at the case where x is an even integer? So I'm going to case 1, when x is, well, I'll write it out in words first. When x is even. All right, so I write case 1, and then I tell the reader what I'm going to be assuming here. And this takes care of, this case will take care of, half the integers. And then I'll do a second case where x represents an odd integer, and that'll take care of all the rest. And then putting the 2 together, right, when we look at both of them together, that'll be a proof for, for every integer. Right? So x is even. By definition, right, when I assume x is even, representing an even number, what does it mean to be even? X equals 2 times some k, and again, when I introduce a new letter, I have to tell you what it is, right? Tell the reader what's going on. For some integer k, plugging x equals 2k into this expression, I eventually want to show that this expression here will represent an even number. So plugging x equals 2k into the expression x squared minus x yields the following. X squared minus x would be equal to 2k squared minus 2k, which is 4k squared minus 2k. And hopefully you can see that I can write this expression as 2 times an integer, right? I can factor a 2 out. 2 times the quantity 2k squared minus k. Right? And I'm just going to put this right now. Usually I write a full sentence for this, but just to save a little time, just a little brace under here and say this would be an integer, wouldn't it? Right? 2 times 2k squared minus k. Since k is an integer, 2k squared minus k would also be an integer, right? Because remember, integers are closed under multiplication, addition, and subtraction. So x squared minus x is an even integer. And I didn't write it, but that's what we're trying to show, right? I probably should have written it for the reader, but we're trying to show that x squared minus x is even. Right? Therefore, or so, x squared minus x is even. Now, usually, right, when you write what you're trying to show, put a little box, but this is only the first case, so the proof technically isn't over. All right, this mini part of the proof, right, this case is over, but the whole proof isn't over, right? So I've only proven this statement is true for even integers, right? For every even integer x, x squared minus x is even. That's what I've proven right here. And then to take care of the rest of the integers, then I'll look at the second case, when I broke up the domain into, I'll look at the odds. Right? So then beneath this, case 2. Right? Case 2, x is odd. I'll write the assumption. Right? And putting these together takes care of all the integers, right? Evens and odds put together make all the integers. So what does it mean for x to be odd, right? By definition, right? By the definition of oddness, x can be represented by, now since this is a separate proof, right? You can think of each case as a separate proof within the proof. I could use k again, right? Normally I wouldn't use the same letter twice, but because it is a separate case, a separate proof, I can use k again if I want to, but just to avoid confusion, I'm going to use a different letter for the integer here. So x is odd by definition. X equals, say, 2m plus 1, right? Remember, it's a multiple of 2 plus 1. Any odd number can be expressed that way for some integer m. Then same deal as before, plugging this into the, I'm trying to eventually show that x squared minus x is even. So I'm going to plug this in to the expression x squared minus x. So looks all pretty similar here, right? Plugging this in, right? X equals 2m plus 1 into x squared minus x will give me the following, right? Yields the following. X squared minus x equals 2m plus 1 squared minus the quantity 2m plus 1, replacing the x's with 2m plus 1. Then squaring this will give me 4m squared plus 4m plus 1, and then distributing the negative here, we got minus 2m minus 1. Combining some like terms, we have 4m squared, just doing some algebra here, plus 2m, and then the 1's are gone. And then look, can't I express this? I'm trying to show that x squared minus x is even. Can I express this as 2 times an integer? Yes, I can, right? Just factoring a 2 out of this. It's 2 times the quantity 2m squared plus m. And again, instead of writing out a whole sentence about how this is an integer, I'm just going to put a little brace under this. Say, hey, we know that m is an integer, so 2m squared plus m, because of the closure properties, will also be an integer. Okay, therefore, x squared minus x is even. So x squared minus x, by definition, is even, right? It would be a multiple of 2. Okay, and since I've shown this for both cases, right, and that takes care of all the integers, right? Case 1 took care of when x was even, the even integers from the domain. Case 2 took care of the odd integers from the domain, and that's the entire domain. All right, and since the entire domain has been accounted for, and I have shown that for every even integer x, this is even, and for every odd integer x, this is even, then we have shown that this theorem is true for every integer x. X squared minus x is an even integer. So I've finished all possible cases. Now the proof is complete, and I'll put the little marker to indicate that the proof is over. Okay. So again, if you have a statement about parity, if you have a statement about evenness or oddness, this might be a good thing to try. Try proving by cases. Look at one case when the integers you're looking at are even, another case when the integers you're starting with are odd. It's a pretty natural starting point. Now, this isn't the only type of proof by cases, as we'll see here in a minute. Okay, so you got that proof that I just did, and there's an animation for it. Right, there is an animation for this. I'll leave that to you to watch. Now, here's an activity where you're asked, hey, if I'm given a certain domain, would the following cases be enough in a proof by cases? Right. So indicate whether the division of each domain is a valid set of cases for a proof. So remember, every single value in the domain has to be accounted for. So if the domain is the integers, right, if they're saying x is an integer, case 1, x is less than or equal to 5, so that takes care of 5, 4, 3, 2, 1, 0, -1, those integers. Case 2, x is greater than or equal to 6. That takes care of 6, 7, 8, 9, 10, and so on. That is all the integers. Both these cases put together make up all the integers. So this would be a valid set of cases if you were doing a proof by cases. All right. Now let's do number 2 here and leave the rest to you. How about if the domain was all real numbers? Not just the integers, but all real numbers, rationals, irrationals, and so on. All right. Case 1, x is less than 0. Well, that takes care of all the negative numbers on the number line, all the negative real numbers. Case 2, x is greater than 0. That takes care of all the positive real numbers on the number line, the positive real numbers. But there's one number that's not being accounted for. There's one number that doesn't belong to one of these cases, and that's the number 0. Right? Case 1 takes care of the negatives. Case 2 would take care of the positives, but 0 is not accounted for. So this wouldn't be complete if I did a proof by cases and the domain was all real numbers and I only did these 2 cases. The proof would not be over. I would have to add a third case to get x equals 0 in there. Okay, so pay attention, make sure, and there can be overlap. All right, there can be overlap, but just make certain that every single number in the domain is accounted for. Right? Or every possibility. Right here, this last one isn't even on numbers. P is a proposition. Case 1, when P is true. Case 2, when P is false. Every single possibility is accounted for, right? A proposition can only be true or false. So this, if I did a proof by cases like this, it would be valid. Right? So every single possibility has to be taken into account when you're looking at cases. Right. So again, I'll leave you to read this, and there's another video here that goes over how to look at this proof. So this is a proof about like groups of people and friends and enemies. It's interesting. But I'll leave it to you to read that one. It's another proof by cases. Alright, so here, I'm going to do this one. I'll do this one on paper for you. And it's another one of those fill in the blank ones with the multiple choice. But, fill in the A, the B, the C, the D, right, and the E. I think I got the 5 there. But let me show you how I would prove this on paper. So here's the theorem stated in this activity. It's every perfect square is either a multiple of 4 or a multiple of 4 plus 1. And I'll refresh your memory as to what a perfect square is. And a perfect square is of the form, say n squared, where n is an integer. Right. So examples of perfect squares, 0 squared is 0 is a perfect square. 1 is a perfect square because that's 1 squared, or negative 1 squared. Right? It's an integer squared. 4 is a perfect square because you can express that as 2 squared or negative 2 squared, right? Some integer squared and so on. So 4, 9, 16, 25, right? Those are all perfect squares. Right? So I guess you could say every perfect square, n squared, maybe I'll add that to the statement, where n is an integer, right? Just stating what n is and stating what a perfect square is. Every perfect square is either a multiple of 4 or a multiple of 4 plus 1. All right, now the domain here is again the integers. Right? The domain is the integers, because like this n that I just introduced has to be an integer. So again, the domain is the integers. Now you can break the integers up into a lot of ways, right? We saw earlier you could break it up into all the evens and all the odds. You could break it up into all the multiples of 3, all the multiples of 3 plus 1, all the multiples of 3 plus 2, right, in those 3 groups. Or all the multiples of 4, all the multiples of 4 plus 1, all the multiples of 4 plus 2, and then all the multiples that are multiples, all the ones that are multiples of 4, then plus 3, into 4 groups, and so on. Again, I think again, it'll be pretty easy to do here. This is just an introductory example. Again, let's break this up into evens and odds again. I'll break this up into the evens and the odds, and we'll see how when I take an even number and square it, an even integer and square it, it'll either be a multiple of 4 or a multiple of 4 plus 1. And when I take an odd number and square it, it'll be either a multiple of 4 or a multiple of 4 plus 1. All right, so again, I write the word proof. We're starting the proof now. And again, if you do some scratch work and whatnot, you got to do that off to the side. But I'm just going to write the proof now. Case 1. Let n be an even integer. Let n be an even integer. Also, start with the evens again. So I've introduced this letter n, told you what it is, wrote the assumptions for my reader. And I guess I also could write that we will show that n is either a multiple of 4 or a multiple of 4 plus 1. Okay. But I'm not going to write that. Right? That's optional. But usually it's courteous to let the reader know where you're going. Right, just as before, what does it mean to be even? Right, by definition, n is equal to, say 2 times k for some integer k. Right, that's what it means to be even. And then I'll look at n squared, right, because this is a statement about perfect squares, integers squared. So plugging this into n squared, I'll just say plugging into n squared yields the following. We have n squared equals 2k squared, which is equal to 4 times k squared. And k squared would be an integer. I'll do this thing again with the little brace. K, since k is an integer, K squared would be an integer. And what I've just shown you is that if I look at an even integer, the perfect square of an even integer, it's a multiple of 4. It does satisfy this here. You know, it's a multiple of 4 or a multiple of 4 plus 1. It's going to be a multiple of 4. So it does satisfy this statement. All right, so in this case, in case 1 here, when I'm looking at the squares of even integers, so we have the n squared is a multiple of 4. Let's see, 4 times k squared. So it's definitely a multiple of 4 or a multiple of 4 plus 1. Remember, to satisfy an or statement, you have to satisfy just one of the statements. Right. All right, so I've proven that this statement is true for even numbers that are being squared. Right, perfect squares where the number being squared is even. Now let's look at the other. Again, so that takes care of half of the integers, and then we'll look at the other case where n is odd. Where I look at the squares of odd integers, and that'll take care of the entire domain, right? Because you can only either square an even integer or an odd integer. Okay, so case 2, and please know that not every proof is going to have just 2 cases, right? There are proofs out there with 3 cases, 4 cases, 1,000 cases. If you look up the proof of something called the 4-color theorem, that was a computer-based proof with, I think it was like thousands of cases. All right, so just because I'm showing you a couple of examples here with 2 cases, right, just make sure you know that that doesn't mean every proof is going to have 2 cases. All right, so this time, instead of looking at n being an even integer, right, instead of looking at the evens, say let n be an odd integer. So I state my assumption. What does that mean? So again, by definition of oddness, that means that n is equal to 2, say j plus 1 for some integer j. Alright, and then just to save a little more time here, so I'm going to plug this into n squared. We'll have this. Then n squared would be equal to 2j plus 1 squared, which would be equal to 4j squared plus 4j plus 1 right after foiling. And do you see that we're going to get here a multiple of 4 plus 1? See, I got the plus 1 here. All right. So we're going to get this down, the multiple of 4 plus 1. I got the plus 1, and then both of these have 4 in common, these first 2 terms. If I pull a 4 out, you'll have the quantity j squared plus j, and that's an integer, right? If j is an integer, then j squared plus j would also be an integer. And then you've got the plus 1. So this statement is again satisfied. The perfect squares when the number being squared is odd will be not a multiple of 4, but it will satisfy the other part, the or, the multiple of 4 plus 1. So in this case, n squared is a multiple of 4 plus 1. And that takes care of all the domain, right? The first case when we squared even integers. The second case when we squared odd integers, right? And that takes care of all the integers. And we have shown that this statement, this up here, we have shown that this is true in either case. So the proof is over. That theorem is a true statement. Every perfect square is either a multiple of 4 or a multiple of 4 plus 1. Okay. Great. All right, so I'm going to fill in that stuff. All right, so now some different kind of statements. Instead of involving evens and odds and the integers, we'll look at some statements involving the real numbers and the absolute value function. All right, now you have to recall the following. They say the following example uses the absolute value function. Remember, the absolute value of a real number x is defined this way. The absolute value of x is the opposite of x if x is negative. So that's like one case. And the absolute value of x is just x itself if x is non-negative, right? If x is greater than or equal to 0. So like another case there. So for example, if x is negative 3, right, then that means x is less than 0. So you have this first case, and the absolute value of negative 3 would be the opposite of negative 3, or positive 3. Right? And if x is positive 3, then x is greater. Hopefully you remember absolute value. Okay, this shouldn't be new to you. Alright, so I'll show you, let's see, we got the proof there, and this proof here. Alright, now this is just fill in the blanks. Okay, so I'll do this first one. Alright, so I'm going to write out this, I'll write out this theorem and show you how we would prove this by cases on paper. Alright, so here's the statement. For any real number x, the absolute value of x plus 5, then minus x after, is going to be greater than 1. And you can test this out, plug in values of x and see if you believe it. Right, the domain here is, this time all real numbers. Right? The domain is the real numbers. And we're going to break this up into cases, into pieces. Now this is a statement involving absolute value. And how absolute value is expressed depends on the value inside. Right, the value inside here is x plus 5. Right, so we're going to break this up into two cases. One, when x plus 5 is a negative number. Right? Remember, the absolute value of a negative number is the opposite of that number. And then 2, when x plus 5 is not negative, right, is greater than or equal to 0. And you see how both these cases, again, I know it's only two cases, just please know that you might see proofs with more than two cases later. This is saying that x is less than negative 5, and this is saying that x is greater than or equal to negative 5. Do you see how every single value on the number line is taken care of, is addressed, accounted for by these two cases? So these are perfectly valid cases to break up the proof into. So I'm going to say proof. So case 1. X plus 5 is negative, less than 0. Or you could say x is less than negative 5. All right, now I'm going to write a few less words than I usually do. I apologize, but don't want this video to run way too long. If x plus 5 is less than 0, I guess then you could say, I will write it actually, then x is less than negative 5, right? I'll keep that in mind. But then you look at this expression here. All right, let's look at this expression here. I'm just going to write a bunch of thens. Then, the absolute value of x plus 5 minus x, this would be equal, remember, the absolute value of a negative number, right? X plus 5 here is negative in this case, is the opposite of that number. So it's the opposite of the quantity x plus 5. And then we have minus x. And this equals, when I distribute and combine like terms, this equals negative 2x minus 5. Right. Okay. And then I can show you that this is greater than 1 using this. Right. So, and this isn't a great proof right now, I'm sorry, but if we start with x is, x has to be less than negative 5, I'll try to get this expression to show up in this inequality. if I multiply both sides by -1, that'll flip the inequality here. I'll just multiply both sides by -2. So I'd have -2x is greater than 10, right? And then if I subtract 5 from both sides, we'd see that -2x minus 5 would have to be greater than 5. So then putting this back here, this is greater than 5, which is definitely greater than 1. Right? That's definitely greater than 1. Right? So we do have the absolute value of x plus 5 minus x being greater than 1 in this first case when x is less than -5. Right? And not a lot of words there, I apologize. You should be writing more words. Again, just want to save a little time here. But when you write a proof for me, please include your full sentences and full explanations. Now the other case, now again, this only takes care of the real numbers less than -5. So I look at the other case when x plus 5 is non-negative. So case 2, right, the proof's not over. X plus 5 is greater than or equal to 0, or x is greater than or equal to -5, right? This takes care of the rest of the real numbers, all the numbers -5 or greater. Well, then if I look at this expression, the absolute value of x plus 5 minus x, that would be equal to, now x plus 5 is not negative, right? The absolute value of a non-negative number is itself. So this would be equal to x plus 5 minus x, which is equal to 5. So the value of this expression would just be 5, which is definitely greater than 1. Right? So in this case, this second case, the absolute value of x plus 5 minus x is definitely greater than 1 as well. And we have shown that, right? We have shown that that inequality is true for all real numbers, right? Both of these cases take into account every single real number. So now, the proof is over, and this statement is true. Okay. So yeah, that there had a little. I probably would have done this on some scratch work, and not actually shown it in the proof, and just kind of said, hey, this has got to be greater than 5 since x is less than -5, and then that's greater than 1. So I normally I would have probably made this some scratch work on the side and not actually shown this in the proof, and then just went straight to here. Okay. So again, you got some absolute value examples there. Now this one involves two variables, right? I'll at least read the first one off here. It says for every pair of real numbers, x and y, the absolute value of x times y is equal to the absolute value of x times the absolute value of y. All right, so since there are two variables, you have, see, 4 cases. Let me show you the 4 cases here, because each variable represented, can either be positive or non-positive or non-negative. So if x is greater than or equal to 0 and y is less than or equal to 0, that's one case. And then when x is less than or equal to 0, y is greater than or equal to 0, that's another. And then here where they both have the same sign. And I'll let you figure out which case which proof for each case would show this statement here. Right, I'll let you fill that in. All right, then the final section, the final part of this section, is on the phrase without loss of generality. And you'll see this written quite often in proofs where there are cases involved. If your proof for one case would look basically exactly the same as another case, but just some variables switched, you can kind of shorten the proof with the phrase without loss of generality. And let me explain that. Let me read through this here for you. So sometimes the proofs for two different cases are so similar that it is repetitive to include both cases. It's redundant. When this happens, the two cases can be merged into one case. The term without loss of generality, sometimes abbreviated WLOG, without loss of generality, or with periods between them, WLOG, is used in mathematical proofs to narrow the scope of a proof to use, to one special case in situations when the proof can be easily adapted to apply to the general case. Meaning, if you did a proof of one case and a proof of another case is basically the same but with just some variable switch, you don't need to do that. For example, for any two integers x and y, if x is even or y is even, then x times y is even. You see the if x is even or if y is even. Well, if you let x be even, case 1, because you got the or here, or will indicate, usually if your hypothesis contains the word or, you're going to have cases, right? This or that. If I go through a case where x is even, I'd have, x equals, say, 2k, and let me actually write this out. Right, I'll write it out and show you why we could use the term without loss of generality for a proof like this. So here's that statement. Again, for any two integers, x and y, if x is even or y is even, again, the word or in your hypothesis will indicate the use of cases most often. So when I go to write the proof, then x times y is even. So here's a long-winded proof of this. Case 1. I assume x is an even number. X is even. All right, that means that, again, I'm not going to write out a lot of words this time, but that means x equals 2 times k for some integer k, and then you plug that into x times y, and that would give you, 2 times k times y, which would be 2 times ky using the associative property for multiplication of integers. Therefore, xy is even, right, because it's 2 times an integer. Okay. And then case 2, if y is even, right, x is even or y is even, that's case 2. Y is even. So that means that y equals 2 times, say, j, or again, since it's a separate case, you could use k again, right, because it's not meaning the same k. But I'll use a different letter. For y equals 2j for integer j, and then you have x times y would be x times 2j, and you can pull the 2 out front, use commutative property and associative property. This would be 2 times xj. And we have 2 times an integer, therefore x times y is even. And I've shown that x times y would be even in both cases, right, when x is even or if y is even. And there we go. Right, I've taken care of every case proffered by the hypothesis. Now, look at these two cases. They look exactly the same, with just some letters switched, right? Basically, throughout this, the case 2 is the same as case 1, but all I did was replace x with y. Yeah, like I said, you could have used k again, right, because it's a separate case. Separate cases is like a separate proof. So if I used k again, it would have been exactly the same, except x and y are switched. Right. So both cases are the same proof with just x and y switched. So if that's the case, if you're doing a proof by cases and you think, hey, this is going to be exactly the same as my previous case, then there's no need to do it. So instead of doing this second case like I did in this, since there's only one case, there's no need to write case 1 now, right? If I get rid of a second case and go to just one case, there's no need to write case 1 if there's only one case. And I just say, without loss of generality, suppose x is the even integer, right? Because if they're saying, suppose this, right? Because if they're saying, if x is even or y is even, well, then x times y is even. It doesn't matter if x or y is even. If one of those is even. So without loss of generality, without losing any generality here, let's just say x is the even one, right? Because if x is the even one, this is satisfied. It's an or statement, right? Remember, an or statement is satisfied if one of them is. So if I just say, hey, if x is even, great, it doesn't matter if y is even, right? And you could say y is even too. Right? It would be the same kind of thing. They have the same kind of proof. Right? So let me read more here. Right? So you see here they say, without loss of generality, assume that x is even, and then they do the stuff and show that x times y is even as well. Right? But yeah, so if the proofs of two cases are again basically the same with just a switch of letters, you can perform this, you can use this phrase without loss of generality to cut down the cases and shorten the proof. All right, so let's see when to apply, without loss of generality. Let's see, can I do it? Can I use the phrase? So consider the following theorem and proof. Can the following two cases be merged with the use of without loss of generality? So the statement is, if x and y have the same parity, right, so they're both even or they're both odd, right, the same parity, then 3x and 5y also have the same parity. Right, so let's read through these proofs. So case 1, x and y are both even, right, and then the other one is x and y are both odd. Since x is even, x equals 2k for some integer k. Since y is even, y equals 2j for some integer j. Then you look at 3x and 5y, and they're both even, right? They're both even. Right? The case 2, x and y are both odd. X equals 2k plus 1 for some integer k. Y equals 2j plus 1. Already they're different, right? X equals 2k is totally different than x equals 2k plus 1. So these are different proofs. One's with evens, one's with odds. These are different proofs. I have to look at both of these cases. Right? You cannot merge them like I did in the paper earlier with the phrase without loss of generality. Right? So I cannot merge these. They are totally different proofs. Right? 2. Again, same thing. Can I merge these cases with the use of without loss of generality? So if x and y are real numbers, then the maximum value of x and y plus the minimum value of x and y must be equal to x plus y. So you see the first case is if x is less than or equal to y. All right, if x is less than or equal to y, then the minimum value of x and y is x, and the maximum value of x and y is y, and so therefore this sum is equal to x plus y. The other case, right, one case is when x is less than or equal to y, the other is when x is greater than or equal to y, right? Because either you're less than or equal to a number or greater than or equal to it. If that's the case, then the minimum value is y, maximum value is x. And see, all that happened here was a switch. It's the same exact proof, right? After you name the assumption, after the assumption, in each case, the proof is exactly the same, only the variables are switched. X replaced with y, y replaced with x. So I could merge these, cut case 2 out, and then remove the remove the words case 1, because again there'll only be one case. There's no need to write case 1 if there's only one case. And then write without loss of generality, suppose x is less than or equal to y. Suppose x is the smaller of the two numbers. And then you get this is a true statement. Right? Because if y were the smaller of the two numbers, it'd be the exact same proof, just with the letters switched. Right? So I could merge these two with the use of without loss of generality. Now you're probably not going to have to do that too often. I mean, then you have your additional exercises. I think maybe one of these later they ask you for the same stuff, but most of them are proofs. So you got your additional exercises. Again, some of these are in your assignment 3. A lot of them are not. You have the solutions you can view. And I say this every time. Please do the proofs. Try to work them out. Try to do these things on your own before you look at the solutions. You're not going to learn anything if you look at the solutions and just copy them. All right. And also, don't just do the ones I assign. I would highly recommend doing all of them. All right, the ones I don't assign. And just to get more practice, get more exposure. The more you do something, the better you get at it. Especially with this proofwriting, the more proofs you read, the more proofs you do, the more proofs you see, the better you'll get. And if this is your first time seeing proofwriting in this chapter, please, if you haven't yet, go back through all the chapter sections in the proofwriting. Look at every single problem. Read every proof you can. Work on every proof you can. Write every proof you can. Because it does take a while to get used to the structure and the form and writing nice, clean, organized, valid proofs. Right. And that's it for section 2.7 here. And that is also it for chapter 2 on proofs. Now that doesn't mean proofs are going away. All right, we'll see more proofwriting throughout the course. And in fact, we haven't even seen all the proofwriting methods. I've mentioned this in an earlier video, but we'll see in a later chapter a method of proof called proof by mathematical induction. And that'll just add to your repertoire of proofwriting methods. That's more specifically for writing proofs involving statements about the integers, but still it is another proofwriting method that we'll come across. All right. So hopefully you got chapter 7. Hopefully section 2.7 is good for you, and this video helps guide you through it. And thank you for watching.